There. During this session, I'm going to relate the equivalence of mass and energy. I'm going to be talking about how mass, much like time, can be dilated. So first of all, some basics. The mass of a body when measured by someone at rest relative to the body is known as the rest mass, whilst the mass, sometimes called the relativistic mass of a body when measured by an observer travelling at a velocity, okay, a relative velocity. So these are the first key terms. So, unsurprisingly, the variation of mass is basically due to time dilation. There's no big surprise there, and the calculation is very, very similar. So what we have is the mass original is equal to the rest mass there, which is MO, and we have the relativistic mass, which is MV, and this is multiplied by the Lorentz constant, the square root of 1 minus v squared over c squared. So that's the formula to try and get us from rest mass to relativistic mass. So let's look at calculating relativistic mass increase. So here we recognize that there's a relationship. The mass of an object is equal to the Lorentz function multiplied by the rest mass. The mass is an object, the mass object measured by an outside observer relative to it, the Lorentz factor. So therefore the mass increase confirms that nothing can go faster than light. So as v velocity approaches c, then the Lorentz factor becomes infinite. So it would require an infinite amount of energy due to the infinite mass to push the object to c, which is obviously something which cannot be done. So therefore creates a natural restriction to the scenario. Things to note here. There's often a flexibility with the units of mass and energy here. The SI unit for mass is kilograms, and for energy is the joules. However, on the scale of subatomic particles, we often use mega electron volts for energy. So the unit comes along when we have mc squared is mega electron volts. Now, for this reason, the masses of subatomic particles are often expressed in mega electron volts per speed of light squared. So using this as an example, the rest energy of an electron is said to be 511 mega electron volts as energy, and its mass is therefore said to be 511 mega electron volts per speed of light squared. So we start to see this equivalence of mass and energy coming through, and we'll talk about that more later on. This all comes from Einstein recognizing that E equals mc squared as a consequence of special relativity. So we can extend this from E equals mc squared, which is the total energy of an object. When an object is at rest, then we find that V equals 0, the Lorentz factor is 1, and E is equal to the rest mass multiplied by the speed of light squared. So Einstein's relationships again, E equals mc squared gives me the total energy, E equals the rest mass squared equals the rest energy, and therefore we could say that the rest energy and then the total energy incorporates relativistic motion. So here's a question. Find the rest energy of an electron and its total energy when it moves at a speed equal to 0.800 times the speed of light. So pause, try and answer this question. So the rest mass, as just previously mentioned, is 9.1 times 10 to the minus 31 times 9 times 10 to the 16, which gives me 8.19 times 10 to the minus 14 joules. To convert that into electron volts, I've got 8.9 times 10 to the minus 14 divided by 1.6 times 10 to the minus 19, which is the charge of an electron, and gives me 0.511 mega electron volts. That's the rest mass. When it's traveling at that speed, what we have here is the Lorentz factor at a speed of 0.8 c is 1.667. So the total energy is 1.667 times 0.511, which gives me 0.852 mega electron volts. Another quick question here. A proton, rest energy 938 mega electron volts, has a total energy of 1170 mega electron volts. What is its speed? So here we're going to recognize that we're going to use the rest mass, which has been given to us, and the total energy. And what we can do here is we can think about the mass as energy. So we have our value for rest mass is 930, or rest energy is equivalent to the rest mass, which is 938 mega electron volts, and the total energy is equivalent to 1170 mega electron volts, which means I can solve that for V, which equals 0.598 times the speed of light. So let's think about this relativistic mass increase. If I have a constant force and is applied to a mass, I'm increasing its kinetic energy according to the relationship force times distance equals work done, and that would be the increase in kinetic energy, half mv squared. Now, this clearly can't go on forever because there's going to be a point when V cannot exceed C. So therefore, the only thing that can be done is that the mass must increase. Okay, this is where the mass dilation becomes really, really important. Think about the increased kinetic energy of body B is equal to the work done causing it to accelerate. So it can be shown that if the relative speed of body B is such that its mass is m, then how we're going to work is the kinetic energy is going to be equal to, or the kinetic energy is going to be equal to mc squared, which would be the total energy, minus the rest energy is going to be equal to the kinetic energy. Okay. Or if we rearrange this, suddenly the kinetic becomes equal to the change in mass multiplied by the speed of light squared. A couple of formulas which come through which are kind of useful here. So kinetic energy is equal to the Lorentz factor minus 1 times the rest mass times speed of light squared, and let's always remember that the kinetic energy is equal to half mv squared. So I said about this a lot. This comes back down to the equivalence of mass and energy, and one of the key things here is that if the force is converted into mass, if we define the total energy E possessed by the body to be the sum of its rest energy and its kinetic energy. And this all comes down to the fact that we find the famous change in energy equals change in mass times speed of light squared, the E equals mc squared formula. Quickly going to talk about accelerating particles, normally because there's often questions related to this. So if a particle is accelerated by a potential difference of v volts, then its total energy will increase by qv, where q is the charge of the particle. If the particle is initially at rest, its total energy is the rest mass after going through the potential difference will be total energy will there be the rest mass plus qv. So that will give me the total energy. Example question here. An electron of rest energy 0.511 mega electron volts is accelerated through a potential difference of 5 megavolts in the lab. What is the total energy with respect to the lab? what is the speed with respect to the lab. So the total energy is E equals rest mass multiplied by the speed of light squared plus QV, which gives me 5.511 megaelectron volts. And what is its speed? Well, if I know, and I'm using the equivalence principle again, 5.11 equals the Lorentz factor multiplied by 0.511. So therefore, if I divide those through, it gives me a Lorentz factor of 10.785. And then that can be solved for V equals 0.996 times the speed of light. And there we are, a quick overview about math.